Well, welcome to Chapter 13, Part 2 Solutions. I'm going to go over some of these at this point. As always, I'll upload a PDF as well. So this problem 35 had a 1 centimeter diameter pipe widened to 2 centimeters, then it narrows to 0.5 centimeters. The liquid was flowing through the first segment at a speed of 4 meters per second, with a speed in the second and third segments. Well, you could think of this proportionally, because if you don't need to handle it exactly mathematically yet, but if it's 1 centimeter diameter and then it goes to 2, that means that the cross-sectional area is going to quadruple because the area is pi r squared, and the radius is proportional to the diameter. So when it narrows to 0.5, it's going to be going 4 times as fast, and so therefore it's 16 meters per second. When it widens to 2 centimeters, it's going to be going 1/4 as fast, so 1 meter per second. For Part B, when you're looking at the volume flow rate, here we actually do have to have exact values. So I'm going to use the radius of this initially. It was 1 centimeter diameter, so it's 0.5 centimeters radius. That's 0.005 meters squared times pi, and then that's 4 meters per second. So that gets me pi times 10 to the negative 4th cubic meters per second. For 37, you've got a pipe and it's got a gauge pressure at the bottom, and you're asked to find the gauge pressure at the top. So since these are both gauge pressures, we don't need to add in atmospheric pressure. But you do need to be careful on the AP exam, because a lot of times they'll ask you for absolute pressure, and sometimes we need to use it for other things when we get into thermodynamics. So we're going to use Bernoulli's equation. The bottom here, the H1 is 0. At the top we've got a speed, bottom we've got a speed. It tells you what those are in both of them. The density of oil is from earlier in the chapter, and you're told the gauge pressure down here is 200 kilopascals. So plug all that stuff in, we get the gauge pressure at 2 is 109,600 pascals. For problem 39, you've got a rectangular trough, and it's 2 meters long, 0.6 meters wide, 0.45 meters deep, completely full of water. One of the trough has a small drain plug at the bottom right edge. When you pull the plug, what would the water be coming from the hole? This is surprisingly a Bernoulli's problem, with many, many things that cancel out. So since both the opening on the side and the top are open to atmospheric pressure, those are the same. The first place up above is at rho GH, but if we have a wide opening, the velocity that goes, like if the tank is much wider than the opening, this velocity is essentially 0, because it's so close to 0 that something close to 0 squared gives us a 0 value here. And then H2 is going to be 0 because that's at the bottom of the tank. So that cancels out. So basically what I have is a potential energy problem, potential energy converting into kinetic energy, which is freaking amazing. It's just that type of problem. And that really shows you how this Bernoulli's equation relates to energy. So essentially we get that it's coming out at about 2.97 meters per second. This particular idea of a large surface and a small hole determining the speed is, I believe, called Torricelli's theorem. I should look that up and see. Let me look that up and see. Torricelli's law? Theorem? Sure. Hey. The speed of flowing under the force of gravity out of an opening tank is proportional to the square root of the vertical distance, h, and blah, 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 blah. So it kind of goes like this. Holes for the jets. These go further. Yep, so kind of neat. Blah. All right, going back to that, you can see what I was watching. This one I mentioned was like a top view. So you've got kind of water. It's a 3 centimeter diameter water line or a pipe. It splits into 2 1 centimeter diameter pipes. Here you're looking at it as a top view. So point A, this was 2 meters per second. You're trying to figure out the gauge pressure here. So the gauge pressure here was 50,000 pascals, 50 kPa. So what I need to really do is figure out the speed here. And I'm going to figure out that speed from the continuity equation. So this pi r squared, 0.015 meters squared times 2 meters per second. I have 2 pipes, and they each have water flowing through them. So I'm going to put 2 in front of this. pi times the radius of the smaller pipe squared times V2. So the speed through each of the smaller pipes would be 9 meters per second. But now that I'm only thinking about pressure, I don't need to multiply by 2 anymore. So I've got the initial condition, which is, I should have written Bernoulli's theorem out better, P1 plus 1/2 density times the speed at the first place squared plus P2 plus 1/2 density times speed at the second space squared. And that gives me 11,500 pascals. So the pressure again is much lower where it's going faster. P65 was the last one. So I said that this was a little bit odd. I think we have, it's a weird pipe, but essentially what we've got is you've got the visual situation, which is shown here, 10 centimeters squared here, 5 centimeters squared here. So although it's not in standard units, they are giving you areas, so you really don't have to calculate that. As long as you know this, you can use those to find the speeds. So the water pressure that exits the air is the atmospheric pressure. So that's easy for the pressure at this point. To find the height of the water column, we need to know the pressure at the start. So that's right here. So now we're going to use Bernoulli's. Well, to use Bernoulli's, we've got to find the speed. So it's A1 times V1 equals A2 times V2. I know that area. I'm trying to find that velocity. I know that area. I've got that velocity. So I find that the velocity here is 2 meters per second. So it's half as fast because the area is twice as much. And again, I don't have to use standard units to figure that out since we're just thinking proportions. So now I'm going to use Bernoulli's equation, which again, I should have written this standard form out for. But P1 plus 1/2 density times this velocity squared is equal to, at this end, this pressure, which is atmospheric pressure, plus rho GH, it's always a 4 meter height, plus 1/2 rho V squared here. So I get that this pressure at this point is 146,500 pascals. That's the absolute pressure. Well, the atmosphere is still 101,000 up here, so I can figure out that the absolute pressure minus the atmospheric pressure would equal rho GH. So this gets back to the P equals P naught plus rho GH. And so that says that this height has to be 4.6 meters. So basically, I'm figuring out the pressure here using a couple different formulas, and I'm getting the height of the water by using atmospheric pressure plus pressure caused by the liquids and the liquid's depth. Hope that helps. Have a great day.